Muchas gracias. Lo siento que no puedo conversar con ustedes en español. Estoy aprendiendo español, pero aprendo lento. No. Aprendo lento y mal. So I'm loving trying to learn the language, but I'm not there yet. So with apologies, I moved to English. There's a wonderful quotation that's usually attributed, probably incorrectly, to the famous Danish nuclear physicist Niels Bohr. Supposedly he said, "It is always hard to predict things, especially the future." Now, in fact, he was wrong. It's very easy to predict the future. Just very hard to be right about your predictions. So despite Bohr's warning, what I want to do is actually give you a lot of predictions about the future. As I've been listening today, I decided to change a little bit the topic that was listed. Instead of just talking about the ethical issues of commercial involvement in genetic manipulation, instead I think it will be more useful and more fun to talk about what we can expect to have happen in the next 10 to 30 years, and what we cannot expect to have happen in 3 biosciences: genetics, assisted reproduction, and neuroscience. So I'm going to talk about those 3, and then at the end I'll come back and point to some ethical issues that run through all of them. So let me start with genetics. In the last 25 years, we have had access to the whole human genome. And if you're old enough, you may remember when it was announced in 2000, everyone said, "We will cure all diseases within 20 years. It's going to be wonderful. We will understand everything because now we have the sequence of everyone's DNA." Well, it turned out to be more complicated. We actually have made some progress on some things, but for the most part, it hasn't turned out as well so far as we'd hoped. I think in the future, we will get better, but we're not going to cure all diseases. People will still get sick, people will still die, people will still suffer, despite however much we know about genetics. But we will be a little bit better at predicting what risks you have, what you should worry about, at diagnosing your problem earlier, and maybe at treating it. For some people, we will get much better, and we already are getting much better. So almost every disease, almost every human condition turns out to have some genetic correlation, some genetic connection. But usually they're very small. And so I have, tengo un resfriado leve. There is a genetic contribution to how likely you are to get a cold or to not get a cold. But it's small. Many genes contribute. Many different factors contribute. But there are about 8,000 diseases that are almost totally caused by genetic variations. The most famous may be things like sickle cell disease, Huntington's disease, cystic fibrosis, beta thalassemia, and there are 8,000 others like them. One piece of good news is we are getting to the point where we have the capability, potentially, of curing those. The Food and Drug Administration in the United States, the medical authorities in the UK, the European Medical Agency in the EU have all recently approved gene therapy for sickle cell anemia. This is wonderful. But most people don't have those 8,000 diseases. Those 8,000 diseases are all rare. Only 1% to 2% of the population has a genetic variation that, as far as we know, leads powerfully to a disease. All of our diseases are connected to our genes, but not very powerfully. So for some people, we will be able to cure their diseases when we couldn't before, and that's a good thing. But we won't be able to cure it for most of the diseases for most people, the things that most of us die from. Things like heart disease, or cancer, or we suffer from depression, or we suffer from schizophrenia, or diabetes. All of these things have genetic connections, but they're fairly weak genetic connections. So I believe we will see great progress in gene therapy for people with particularly powerfully genetic diseases, but only limited progress for gene therapy for diseases that are more common. We will have progress, but it's not likely to change our world enormously. On the other hand, this kind of therapy, this kind of treatment, is less controversial than some, because if you change my genes, let's say I have sickle cell anemia, you change the genes in my bone-making cells, blood-making cells in my bone marrow. It happens to me, but then when I die, it's gone. It doesn't pass on to my children and my children's children. Much more controversial, and so that's called somatic cell genetic engineering, when you're changing the somatic cells, the cells of the soma, of the body. The alternative is what's called germline genetic engineering, where you're changing the germline. Almost all of the cells in our body are somatic cells, except for half of you, eggs, and for the other half of you, sperm. Eggs and sperm are germ cells. If you change the germ cells, or if you modify a human embryo at an early enough age, all of their cells, including their germ cells, will be changed. And that change could pass on to the next generation and the next generation and the next generation, none of whom volunteered for that. If I get stem cell therapy myself, I volunteered. I am, I think, a competent adult. I listened, I made a decision, I volunteered. An embryo can't give informed consent. So there are lots of reasons why this germline gene therapy, germline genetic engineering, is much more controversial. It became not just hypothetical, but real 5 years ago, a little more than 5 years ago, when a Chinese scientist named, and if any of you understand Chinese, please forgive my terrible accent, Hu Zhangkui, announced that 2 babies had been born where he had genetically changed, edited their embryos before the embryos were put into their mother's uterus for birth. His experiment was awful. It was unethical. It was illegal. Chinese court sentenced him to 3 years in prison. We still don't know what happened to the babies. The Chinese government has been completely unwilling to say anything about whether they're alive, whether they're dead. It says it's for privacy grounds, which I kind of understand. But we don't know whether how this experiment worked, whether it worked well for the girls or poorly for the girls, 2 baby girls. Babies, they're now 5 years old, and we still don't know anything about them. So germline therapy, germline genetic engineering, much more controversial because it affects future generations. The somatic cell therapy isn't very controversial. We're still fighting about the germline therapy. Right now, there's really no fight in that everyone agrees it hasn't been proven safe. And if it hasn't been proven safe, don't do it. But if it is proven safe, some people say, yes, in some circumstances we should do it, and other people say, no, we should never cross that line. That issue is still being fought over. But for both somatic cell and germline, there's another issue. I've been talking about it with respect to diseases. But I think what bothers people more is it being used for enhancement. So think about bicycle racers. Bicycle racers 30 years ago would take blood and put it into their veins before a race. This would give them more red blood cells, more oxygen carrying capacity, which would let them go long distances more easily. The sports authorities outlawed that. Maybe effectively, maybe not effectively. So they went from blood transfusions to a new drug called erythropoietin, which also increases your red blood cell count. And so the authorities outlawed that. And some people found ways to cheat that. Now, somebody might say, well, why don't we just change your genes? We know of genetic variations that increase the number of red blood cells you get. In fact, there's an Olympic medalist in cross-country skiing from Finland who had a natural mutation that gave him more red blood cells. So why not do gene therapy to enhance? Well, we don't really know what all it does, and many of that man's relatives died early from strokes, as did many of the bike racers, otherwise very young and healthy bike racers, died from strokes at 25 after they'd given themselves erythropoietin or new red blood cells. So we don't know the issues, but the broader point is, there's a lot of interest in genetic enhancement, except we don't know how to do it. We don't know how to make people smarter. We know genes that make people less smart, but we know almost nothing about genes that make people smarter, genetic variations that make people smarter or more athletic or more musical or more handsome or good looking, bad looking. We don't know. And for the ones that involve the mind, the ones we care the most about that involve behavior, we may never know, because brains are really complicated. Brains are infinitely complicated practically, and we may never learn what genes make people smarter. I think we certainly won't during my lifetime, and maybe not during any of your lifetimes. So I think the germline issue is going to be fought over. I don't think it's going to be very important because there are alternative ways for parents to reach the same end. An important one is called PGT, pre-implantation genetic testing. You have to go through IVF, in vitro fertilization, and when the embryos are in a dish for their first 6 days, you do a genetic test on the embryos. You say, this embryo would get cystic fibrosis. We're not going to transfer that. This embryo has a high risk of Alzheimer's disease. We're not going to transfer that. These embryos look good. We'll pick them. This sounds like science fiction to people. It's been done clinically since 1990. The oldest baby born this way is in her early 30s and is a scientist. Nowadays, in IVF in the United States, more than half of the cases of IVF use this sort of pre-implantation genetic testing. And I think it's going to get bigger and bigger, but it's never going to be such a huge deal because IVF is a pain. It's expensive, it's unpleasant, it's risky. Making babies by sex is not always unpleasant, risky, or expensive. Making babies by IVF is always unpleasant, risky, and expensive. So unless IVF gets easier, I don't think we'll see a lot more PGT, but let me move to assisted reproduction. IVF is going to get easier because using stem cell technologies, scientists are going to be able to already are able to take skin cells from you, turn them into something called induced pluripotent stem cells, thanks to a Japanese scientist named Shinya Yamanaka. Those can become every cell type in your body. Brain cells, heart cells, liver cells, kidney cells. Eggs and sperm are cell types. And 2 Japanese scientists have taken skin cells from mice and made mouse sperm and mouse eggs and mouse puppies. In fact, last year, they took skin cells from a male mouse and made mouse sperm. They took skin cells from a male mouse and made mouse eggs. And they made mice puppies with 2 fathers and no mothers. This is called IVG, in vitro gametogenesis. I think this is going to be maybe the biggest bioscience revolution in the next 20 or 30 years. Why will people do it? Millions of couples who cannot have children because the man doesn't make sperm, or the wife doesn't have eggs, or the wife has eggs but they're too old. They desperately want to have children. This could give them that opportunity. Millions of gay and lesbian couples who'd want to have a baby that's half one and half the other. This would give them that opportunity. So I think this is going to happen. I wrote a book about this. I wrote a book about He Jiankui called CRISPR People. This book is called The End of Sex, about IVG. And it's fascinating. The possibilities are fascinating. One of them, though, is that with IVG, sorry for all the acronyms, IVF becomes much easier. Almost all of the expense and all of the discomfort and the risk in IVF is egg harvest. Sperm harvest, pretty easy. Egg harvest, difficile. So if instead of egg harvest involving 5 weeks of injections and powerful hormones, you just take a 2 millimeter punch biopsy of skin cells, turn those into eggs, IVF looks pretty good. And I think in the next 30 years or so, most people in countries with good health care will make their babies in a clinic so they can go through PGT, pre-implantation genetic testing, to avoid that 1 or 2% of babies who would have a serious genetic disease. And I think governments and health insurers will pay for it because it will save them money. Raising a child with a serious genetic disease is expensive. Avoiding such a child, a lot less expensive. Last topic, and I'm running out of time. Neuroscience. I already mentioned, I think the brain is maybe the most complicated physical object we know of in the world. You've got roughly 90 billion neurons. You've got roughly 10 trillion connections among those neurons. We now know infinitely more than we knew 30 years ago. We now know pretty much still zero. Not quite. Lots of neuroscientists have done a lot of great stuff, and Stanislaw Dehaene, who's speaking on Friday, is one of the world's leading neuroscientists. Go to that talk if you can. We're learning a lot more, but there's a lot more we don't know. However, the possibilities are scary. What if you could put a cap, una gora, on someone that includes an EEG, an electroencephalogram, and can tell whether or not you're sleepy or alert? There are companies in China and in the United States that are forcing their workers to wear this because they want to know if the truck driver is sleepy or the truck driver is alert. Makes some sense. If I were a truck driver, I'm not sure I would want to wear it. What about using this for lie detection or determining whether or not somebody's in pain? As we learn more about how the brain works in order to treat diseases like depression or schizophrenia, maybe that knowledge would let us change people's behavior in other ways. Make criminals less likely to be criminals in the future. Make drug addicts not addicted. Make conservative people more liberal, or liberal people more conservative, and religious people less religious, and non-religious people more religious, and change sexual orientation. We don't know how to do that today. We may never know how to do that. But it's no longer crazy to think that this may happen. I highly recommend a book by my friend Nita Farahani at Duke University, just came out, called The Battle for Your Brain, which goes through these and many other concerns. And here, felicidades a Chile por la primera ley de neurorights. So Chile passed the world's first law establishing neurorights. It won't be the last law. It may not be the best law. Laws change. You learn more. But there's never a better law unless there's a first law. You never get a second law unless you have a first law. And so I'm very happy that Chile took that step and made a neurorights law. This is another area that we need to watch. I have less confidence in my prediction about what will and won't happen, except that it will be important and we'll need to watch it. Last points. What should we mostly worry about? 3 things with new biosciences. First, always safety and efficacy. People don't think about safety as an ethical issue, but it's profoundly unethical to do something unreasonably unsafe to somebody, or to charge somebody money for something that won't work. That's unethical. We need good regulatory bodies to make sure that things that are being sold, often to desperate people, actually work and are safe. Second, access. Remember the sickle cell gene therapies I mentioned? They cost $2 to $3 million per person. If you're in a country with good health plan, maybe the health plan will pay for that. But that's a lot of money even for the health plan. In the United States, there are 100,000 people with sickle cell. Treating all of them at $2 million a year, that's $200 billion, which is a lot of money. And even then, 90% of the people with the disease don't live in rich countries. People in the Central African Republic, or in Laos, or in other places in the world with high levels of these hemoglobin diseases, they can't afford it. Their governments can't afford it. It is really profoundly ethically troubling to have something that can save someone's life, but they can't get it because we can't afford it. They can't afford it. So that's the second problem. And then the third problem ties into what my friend Carter was talking about. There will be issues about the extent, whether there are boundaries we should or should not cross. Are there limits to being human? Are there limits to what we should do with animals? Are there things that would be playing God that we shouldn't do? That's going to be a discussion we're going to have. Personally, I think the questions about safety, efficacy, and access are more pressing and more immediate and more important, but these are also important questions. They won't be easy questions. People will disagree. I agree with much of what Carter said, but I disagree with some of what Carter said. And I'm sure he would disagree with much of what I would say on some of those topics. People won't agree. Different countries won't agree. Different cultures will have different views about what's right and what's wrong, and that's okay. Different countries can do different things, but what's not okay is if countries pay no attention to this. We need to have those conversations. We need to think about what we want to do because the science is not stopping. So this is an amazing time to be alive, for good reasons and bad reasons. This is a particularly amazing time to be alive and to be interested in biology, because our knowledge of biology is expanding enormously. And although AI is the current flavor of the month, we aren't computers, we are biological mechanisms. Biology is closer to us and what we are than artificial intelligence is. We should and will care about it, and it's a wonderful time to watch what happens. I have disregarded Bohr's advice and given you lots of predictions. I am absolutely confident that some of my predictions are right. I'm equally confident that some of my predictions are wrong. And finally, I'm confident that I don't know which is which. But it'll be a lot of fun over the next few decades seeing what happens. Thank you so much for your time and attention.